Okay class, welcome to our session for today. And this is design of steel structures, and I'm Engineer Ranjan R. Garming. So we are going to discuss now compression members, the design concepts. So we will be using the same compression members concepts in steel design. So we have learned that in load resistance factor design we have Pu is equal to the phi times the nominal strength Pn, wherein phi for buckling is equal to 0.9, while that for ASD we have an allowable strength of 1 all over beta times the nominal strength Pn, wherein our beta is 1.67 for buckling. Hence, PA can be simplified into 0.6 of the nominal strength. So recall that Pn is equal to FCR times Ag. FCR in here is the Euler's buckling stress. So FCR is dependent on the Euler's buckling stress Fe is equal to pi squared E all over L all over R. Now L all over R is synonymous to that KL all over R. So of course, utilizing our slenderness factor, we're going to compare the slenderness factor or the slenderness ratio to that of the expression 4.71 square root of E all over Fy. So this is in accordance with the requirement of the National Structural Code of the Philippines 2015 edition. So in the case where the slenderness ratio is less than Cc or 4.71 square root of Fy, it can be classified as intermediate column. So the mode of failure will be inelastic buckling. So in this case, we are going to use FCR is equal to 0.658 raised to Fy all over Fe times the yield strength Fy. On the other hand, if our slenderness ratio will be greater than 4.71 square root of E all over Fy, it is classified as long column, and the mode of failure will be on elastic buckling, wherein FCR to be used will be equal to 0.877 of the Euler's buckling stress. So in the design, we need to compute the required Ag because we have a given loading. So in the previous sessions, we are actually calculating for the Pn, but this time we are doing back calculation of the strength of the chosen member, okay, the strength of the chosen member, so that it should always exceed than that of your required loading. So meaning your chosen member or the trial section should be adequate enough to resist the required loading. So as for the design steps, instead of having a back calculation using these provisions, of course, the procedure may be now tedious because initially we need to calculate for the comparison of the slenderness ratio and that of the Cc and determine whether it is intermediate or long column so that we can use the appropriate expression in calculating for FCR. Now instead of this procedure, we are going to have an assumption FCR is equal to 0.5 of Fy. Now this assumption is actually based on arbitrary choice based on experience. Now from that assumption, FCR is equal to 0.5 Fy, we can already calculate right away the required Ag, because Pu here or Pn will be given in this case. So the third step is to choose from the steel tables the nearest area greater than the required Ag. So of course, in consideration of the lightest section. So the final step will be checking of the adequacy using the procedure in this slide. So let us take that into examples. First, we have a column effective length is equal to 7 meters. Using both LRFD and ASD, design an A36 steel wide flange column with the nominal depth of 410 millimeters that can resist service loads of 400 kN dead load and 900 kN live load. Also check section against local stability. So I think this last phrase will be discussed separately on our next topic, which is local stability. So in the meantime, we're going to treat this problem using the steps enumerated a while ago. So first, in here we assume that FCR is equal to 0.5 of Fy. So this is an arbitrary choice. So applying that formula, we can get right away the FCR. Now this FCR here is not actually the value of the FCR, but this is intended for trial section only. So from here, we note that the nominal strength Pn is FCR Ag. Okay, and then we solve the required gross area. Of course, LRFD would have its factored loads. Okay, so from the given, okay, so Pu is equal to phi Pn, wherein phi is equal to 0.9. Okay, so we have here the factored load, 1.2 dead load and 1.6 live load. So we just apply that load factors into our given loadings. We'll have 1920 kilonewtons. So substituting that into the equation of LRFD, of course we must have to multiply that by 1000 to make it in newtons. Okay, now Pn is actually FCR Ag. Okay, and of course the estimated FCR for a while is 124 Ag. So from that we can now estimate the gross area requirement from the loading, and the next step will be choose from the steel tables the nearest area greater than the required area. Notice here that we need 17,000 plus for this. Hence, in the problem, we are focused only on the wide flange steel column with a nominal depth of 410 millimeters. So, from the table, we look into the sections of W410 with various unit weight in kilogram meter. So in here, of course, W410 by 149 will have the area that is larger than 17,000 plus. So if you notice, we have here an area of 19,000. So we just get those data with the radius of gyration along the x and y axis. So the area gross is 19,000 millimeters squared with the radius of gyration of 180 along x, and along y we have 63.9 millimeters. So with that, we now check the adequacy. Of course, the selected trial section is 410 by 149 with the following properties. Of course, in here, we are concerned with the maximum slenderness ratio. And of course, the maximum slenderness ratio, we're going to choose here the lowest radius of gyration from the trial section. And that is actually acting along y in this case. So we apply the formula. So we use slenderness factor K of 1. So we substitute the length of 7,000 and then Ry of 63.9. We come up with the maximum slenderness ratio of 109.55, which is actually within the limits of 200, and that would be okay. So next step is, of course, to calculate CC to have a comparison to the computed maximum slenderness ratio. So this is equal to 4.71 square root of E all over Fy. So we just apply that. Okay. So this is equal to 133.76. So obviously, your KL all over R is less than your CC. Therefore, it will fall under intermediate column with the mode of failure of inelastic buckling. Hence, we utilize the formula for FCR for this trial section with that expression. So of course, prior to that, we need to compute for the Euler's buckling stress. So we just substitute the calculated slenderness ratio and the modulus of elasticity given 200,000. Therefore, the Euler's buckling stress is equal to 164.48 megapascals. And then from that, we can now work on this equation, substituting the value of Fe and Fy. We find that FCR is equal to 131.94 megapascals. So note that once we have obtained FCR, we are now ready to compute for our nominal strength with this formula here. Okay. So Pn is equal to the calculated FCR times Ag for the trial section, 19,000. So we come up with 2,506,960 newtons. Hence, by LRFD, note that our design strength should always be less than or equal to phi Pn. Therefore, phi Pn is equal to 0.9 of 2,506,960. So therefore, this must be equal to 2,256,174 newtons, which is actually equal to 2,256.17 kilonewtons, which is greater than 1920 kilonewton. Hence, the design here is adequate. Therefore, we cannot still yet choose 410 by 149 as the final trial section or the design section, because we still need to check the second to the lowest section, because it is assumed here that it is always that the most economical design is the lightest one. Okay. By the way, the trial section 410 by 149, 149 indicates the weight in kilogram per meter. Okay. So therefore, we check the next section, and that section is 410 by 132. Okay. We have an area of 16,900 and Rx of 178 and Ry of 63.2. So we do the same procedure. Okay. We check the adequacy of the trial section. So this time it is 410 by 132. Of course, KL all over R, the slenderness ratio considers the maximum. So if we want the maximum, we choose the lowest radius of gyration from the trial section, and that is actually along Y. Okay, we just substitute the formula and we come up with 110.76. And still that is within the limits of 200, and that is okay. So again, CC will be computed, and I think this will not change. Okay, we have 133.76. So KL all over R still is less than your CC. Hence, it is classified as intermediate column with mode of failure of inelastic buckling. Just the same, we use this formula for that, and we use the Euler's buckling stress. Okay, take note here that we need to change the slenderness ratio, because eventually our radius for gradation is different. Okay, but it is near to that of the first trial section. Okay, so the Euler's buckling stress will be 160.9 megapascals. So we continue, substitute the values, and the FCR will be equal to 130.1 megapascals. Okay. So once we have that FCR, we compute our nominal strength by multiplying it to our gross area. So I think this should be 16,900. So this is 16,900. So we come up with 2,198,738 newtons. Hence, by LRFD, so PU should be always less than or equal to Vpn. Okay, wherein Vpn is 90% of that nominal strength. So we come up with 1,978,863.84 newtons. And that is equivalent to 1,978, which is still larger than 1,920 kilonewtons. So therefore, design is adequate. So As per observed now, we can still use as trial section of 410 by 132 for this loading using LRFD. So at this point, we can conclude that the most economical design section for this is 410 by 132. Now, moving on to the ASD method. Okay, so first step is the same. Step 2, solve the required gross area. Now, this time ASD will be in terms of the allowable load of the 60% of your nominal strength PN. Okay, so this time we do not have any factored loads, so it is just simply the sum of your loadings, 400 plus 900, that is equal to 1,300 kilonewton. So that will be equated to our 0.6 of PN, wherein PN is FCR times AG. Okay, so the estimated FCR is 124. So the required gross area is 17,473.12 square millimeter. So we move on to step 3. Of course, step 3. So from our calculation a while ago, I think we should go directly to this trial section 410 by 132 with the corresponding properties, the area, and the radius of gyration along x and y axis. So a similar procedure will be performed here with that trial section. So of course, we choose the lesser radius of gyration, and it is acting along y-axis. So we yielded to 110.76, and still that is within the limits of 200. So we use the same CC here and compare, and that is intermediate column, wherein FCR will be given by that equation. We calculate the Euler's buckling stress. Again, take note that in here we substitute the slenderness ratio maximum. So we continue. So the nominal strength will be given by that equation. So 130.1, 16,900. So PN is equal to 2,198,738 newtons. So what is different here is that ASD, actually ASD, will be in terms of allowable load, which is supposedly less than or equal to 0.6 of your nominal strength. So your 60% of the nominal strength will be equal to 1,319,242.56 newtons, and that is equivalent to 1,319.24 kilonewton, which is greater than 1,300 kilonewton. So therefore, your trial section 410 by 132 still is adequate. Okay, so that ends our session for today. So thank you and have a good day, class.